We're going to discuss the Baire Category Theorem in complete metric spaces. Before we do so, it's a good idea to recall a couple of pieces of terminology. So first of all, let's begin with everywhere dense. So if X is a metric space, obviously this can be given in more general topological spaces. Then a set D, which is a subset of X, is called everywhere dense. When for every open non-empty set U, next, the intersection is non-empty. So in other words, our everywhere dense set meets every non-empty open set. It has at least a one point of intersection with every non-empty open set. And on the other hand, we have the can't really say that this is the complete opposite, but it's pretty much a property that characterizes a set which is pretty far from being everywhere dense. So again, let X be a metric space. Then a set A is called nowhere dense if a subset of X, of course, if its closure has empty interior. So in other words, there will be plenty of open sets that are not being intersected by the set A or its closure. So let's give some examples. So, I mean, it would be a good idea to look at R. So everywhere dense sets in R are obviously the set of rational numbers, the set of irrational numbers, the set of algebraic numbers, any shift of the set of rational numbers. So all of these are everywhere dense sets. If we want to find nowhere dense sets, we can take the set of natural numbers, the set of integer numbers. A much more interesting example would be the Cantor set, which is uncountable. So these are nowhere dense sets. Now, what would be an even larger set is to consider an open everywhere dense set. So how do we construct something like that, which is not the whole real line? Well, I mean, we can find trivial examples such as take R and omit a discrete subset of points like the natural numbers or the integer numbers, but we can have much more interesting examples if, let's say, we take the set of rational numbers, and around each rational number, supposedly they're enumerated, we surround each rational number according to its enumeration with an interval of length 1/2 to the n. So something like, so Rn will be surrounded by Rn minus 1/2 to the n plus 1, comma 1 Rn 1 2 to the n plus 1. So then we're going to get an open set, obviously, if we take the union of all these subsets. That is certainly dense because it contains the set of rational numbers, and obviously it forms an example of everywhere dense set. It's not the whole real line, since the lengths of the intervals that we choose converges, and that couldn't have been everything. It's not so easy to visualize it, but it's a fun set to consider. With this preparation, we're now ready to give the statement of the Baire Category Theorem. So, theorem. Let X be a complete metric space. We will give two statements. Each one of these statements is usually referenced as the Baire Category Theorem. Then the intersection of a countable family of open everywhere dense sets is everywhere dense. And second, the countable, or the union of a countable family of closed nowhere dense sets has empty interior. It's kind of interesting to notice that the two statements are easily equivalent to each other. And the reason for that being that the complement of an open nowhere, oh, I'm sorry, everywhere dense set is a closed nowhere dense set, and vice versa. So usually when we have a set that cannot be written as the union of a countable family of closed nowhere dense sets, this is called of the second category. If it can be written as such a union, then it's called of the first category. So we could paraphrase the Baire Category Theorem by saying that a complete metric space is of the second category. So again, so first category means countable unions of closed nowhere then sets, and their subsets, one might argue. And second category, everything else. Now, this theorem becomes very relevant in functional analysis, where we try to engineer some proofs by using such sets. And of course, the three big theorems in functional analysis, fundamental theorems in functional analysis, the open mapping theorem, the closed graph theorem, and the Banach-Steinhaus theorem, or the uniform boundedness theorem, are all consequences of the Baire Category Theorem. And obviously, the Baire Category Theorem can be used in, for example, other fun cases. So let me finish with this. So take the set that I constructed a moment ago, which was to take the set of rational numbers and surround each rational number by an interval of that length. Call the set A1, okay, or U1. And now do the following. Construct U2 by taking all the intervals and cutting their radius by half. Then U3, take U2, take the intervals, cut the radius by another half. So in other words, you keep getting intervals surrounding every rational numbers that have shrinking radii. You could ask, is it true that the intersection of all these sets is just the rational numbers? Could this be true? Because you keep shrinking the intervals that you get around each point. And the answer is, of course, no, because if that was the case, then you could say take another countable family, which is the sets that consist of the real line except for a rational number, this countable family, and then the intersection of the family that you have and this new countable family, all of which can be arranged, of course, in a countable family, would be empty. And that's not possible in a real metric space like R. So there are some fun things and much more to be done with the Baire Category Theorem. It's not necessarily a theorem that is appreciated the first moment one sees it, but as you go deeper and deeper into the study of real analysis and other disciplines that require real analysis, you get the idea of how important that theory is. And that's all. Thanks for watching.